Hello everybody, I'm going to talk today about self-similar solution of time and space fraction subdiffusion equation. This work is joined with Erkan Karimov. Here's my outline. First, I'll give you some preliminaries related to fraction derivatives and recall some definitions for similarity method. Then second and third point are the main results. So we discussed fraction differential equation involving Hilbert derivative, and also we consider a fraction differential equation involving Hilbert operator. We begin by recalling some definitions related to Hilbert fraction derivative. So the right-sided Hilbert fraction derivative of order alpha, where alpha between n minus 1 and n, it is given in this form, where I represent the Riemann-Liouville fractional integral. In particular, for alpha between 0 to 1, it is given in this form, just by plugging n equal to 1. Then one can write it on this form, where d gamma represent Riemann-Liouville fraction derivative. And have to mention that for delta equal to 0, the Hilbert fraction derivative is reduced to the Riemann-Liouville fraction derivative, while for delta equal to 1, Hilbert fraction derivative is reduced to Caputo fractional derivative. We need the inverse property of Riemann-Liouville of Hilbert fraction derivative. So the inverse of the Hilbert fraction derivative is the integral fractional Riemann-Liouville fractional integral. Also, we need to recall definitions of Ehrlich-Koper fractional integral. So we consider the left-sided, and we need also to define the right-sided fractional Ehrlich-Koper fractional integrals, and they are given by these formulas, where delta positive, gamma belongs to R, and beta bigger than 0. Also, we need to recall Ehrlich-Koper fractional derivatives, the left-sided also and right-sided, and they are given by these forms. Also, one can recall the inverse property that we recall the inverse property, where the Ehrlich-Koper integral is the inverse of Ehrlich-Koper fractional derivative. We need also to recall generalized right functions, which is given by this series, where A and B belongs to C, and U and V belongs to real numbers. Now, before discussing the similarity method, I have to mention that the idea of least symmetry groups approach have been extended to fraction differential equations. So roughly speaking, one can say that the symmetry group of differential equation is a group acting on the dependent and independent variables, which transform the solution of the equation to other solution. Here we focus on the similarity method, and we consider special case of scaling transformation. Using this transformation, we can transform our partial differential equation to ordinary differential equation, of course, with the new variables. So here we start by determine. So we need to determine our scaling transformation. So usually we choose them in this way, where A and B and C are arbitrary constants. Then our BDE, if u equal to 0, is invariant and under one parameter family T lambda, which is given by this transformation. Then this transformation takes any solution u of BDE to a solution u bar of the same equation. So these transformations will leave the equation unchanged. And we need to recall that the new parameter eta is invariant of the one parameter of family T lambda, if it is unaffected by the transformation. So usually this eta, we call it the similarity variable. Our first problem is to consider the partial differential equation with Hilbert fraction derivatives in time and space. Of type, we consider Hilbert of type delta, and for time we consider the order alpha between 0 to 1, while for space we consider it beta between 1 and 2, and we consider these conditions, and we'll see later why we need these type of conditions. So we start by determining our independent and dependent variables. So we start by this transformation. We substitute this transformation in time fractional derivative. Using change of variables, we end up that the time fractional derivative can be written on this form. While for space, doing the same or repeating the same procedure, we end up with this one. Now substituting the transformed fractional derivatives in the original equation, original BDE. So our transformation will keep the differential equation unchanged. So we need this relation that B equal to beta over alpha, okay, in order for these equations to equal to 0 or this relation to be whole or they are equivalent. So we choose our scaling transformation on this form, where eta is now the new variable. Now we are going to substitute this transformation in our differential equation. So we substitute this on the Hilbert time fractional derivative, and now we do substitution of variables. Then we end up with the Early-Cooper fractional integral. So this only for the first derivative. Now substituting back and finding the first derivative, this one can be written as Early-Cooper fractional derivative. Repeating the same procedure, repeating the same procedure for the second integral, we end up with this fractional derivative after using this transformation. So now our time fractional derivative is written in terms of Early-Cooper fractional integral and Early-Cooper fractional derivative. We do the same for the space time fractional derivative, and using the change of variable xi equal to st minus alpha over beta. Then we end up that the space fractional derivative can be written on this form. Now substituting back the time and space fractional derivative, so our BDE now is transformed to this ordinary differential equation, which have new variables, which has new independent variable is eta. Our results can be summarized in the following theorem. So the transformation given by 2 reduced our partial differential equation to the ordinary differential equation with these conditions after doing the transformation. Now our aim is to find the solution of this ordinary differential equation. So we are going to use the inverse property of Hilbert fractional derivative. So we apply Riemann, as we said before, that the inverse of Hilbert fractional derivative is the Riemann-Liouville fraction integral. So we apply I beta to both sides. So our equation using the inverse property can be written on this form. Then we use successive iteration method to solve this equation. So we start with u0. So u0 is given by the first terms, and they are power functions. And un, or nth term, can be written in this form. Now we need to use the following properties. So we need the Early-Cooper fraction operators of power function. And we start our calculation by finding u1, which is written in terms of u0, as we see here. Now, since we know now that u0 is power function, this is two terms, but they are power functions, we can use the properties of Early-Cooper fraction operators of power function, and also we find the Riemann. So doing the calculation, we end up with u1, and it is given on this form in terms of gamma, in terms of eta. We do the same for u2, we do the same calculation, we end up with this form, and then we need to find another term. So we get u3 again, and now we can write the general term un in the series form. So case start from 0 to n. Now as n goes to infinity, this series is converging to right function. So this one is u eta, the solution of ordinary differential equation. Substituting back on the transformation, we get the desired solution. So our solution of partial fraction differential equation with conditions 4 and transformation 2, we get these solutions in terms of eta. But here we have to keep in mind that eta is xt to the power minus alpha over 2, and now it is written in terms of right function. We have just to mention that for delta, equal to 0, which is, I think, in this, for delta equal to 0, our Hilbert fraction derivative is reduced to Riemann. So this solution is concise with the solutions found in the literature for Riemann, for the partial differential equation involving Riemann-Liouville fraction derivative, and also it's concise with the solution which involves Caputo fraction derivative when delta equal to 1. The second problem, we consider the Haber-Bessel operator, and it is written, consider Haber-Bessel operator or alpha between 0 to 1. And the right-sided derivative is the Ehrlich-Hubbard fraction derivative, so we consider this PDE with these conditions. We are going to solve this problem, and Haber-Bessel is defined on this form, which is in terms of Ehrlich-Hubbard fraction derivative. Regarding the solution, we are going to do the same as we did for the previous problem. So we start by finding first our transformation. So we get the same transformation as before, and then substituting back this transformation, our BDE is converted to the ODE, and then we solve the ODE using successive iteration method. So our solution is written in terms of right function as the previous problem. That's all my presentation, and thank you for listening.